Hello, everyone. Welcome to another lecture. This one is going to be on the common ion effect in acid-base equilibria. We're going to show you today how you can prepare a mixture using two solutions. And this mixture is special in that it can resist a pH change if you add either an acid or a base to it. So this type of mixture is absolutely essential to all life forms because many chemical reactions happening inside living systems create changes in pH that have to be controlled by buffers. So we'll talk about buffers. So our first example is we're going to make a solution by mixing two solutions together. Our first solution is 50 milliliters of a 0.20 mole per liter solution of acetic acid, which is a weak acid. Again, it's found in vinegar, formula HC2H3O2. Now, if we take the acetic acid and mix it with a solution that contains the negative ion from the salt, and this negative ion is the same ion that's produced in the equilibrium of acetic acid, we end up with such a mixture. So let's take a look at the dynamics of this actual mixture. So when we mix these two solutions together, we get a changing of the concentrations, and that's because we're diluting them. We've taken 50 milliliters of the acetic acid and mixing with 150 milliliters of the sodium acetate. So we have to consider that the concentration changes because the volume changes. So initially, the volume of the acetic acid is 50 milliliters, which I'm going to write as liters. Its concentration is 0.20 moles per liter. So we can calculate the number of moles by multiplying concentration by the volume. And you end up with the number of moles of the weak acid, the acetic acid. Similarly, let's do the same for the sodium acetate salt solution. So the volume of the solution is 150 milliliters, which I've changed to liters by dividing by 1,000. And the concentration of this salt solution is 0.40 moles per liter. So the number of moles, again, can be calculated by multiplying the concentration times the volume. So we end up with 0.06 moles of the sodium acetate, and we end up with 0.010 moles of acetic acid. So when we mix the two together, we're going to end up with a solution that has the weak acid and the salt containing the negative ion from the weak acid. In this case, it's the acetate ion. The sodium ion will be in the solution, but it has no effect on the pH. Since it's only got a 1+ charge, it doesn't hydrolyze water, as we talked about in a previous lecture. So we're really going to focus now on the concentration of the acetic acid. We know the number of moles. We calculated it, but the volume changed because we added 50 milliliters to 150 milliliters. The total volume is 200 milliliters, expressed in liters as 0.200 liters. When we divide those two, we get 0.050 mole per liter of the weak acid acetic acid. And the concentration of the sodium acetate calculated the same way. The number of moles we calculated divided by the volume of the two solutions added together, and we get the concentration of the sodium acetate, 0.30 moles per liter. So we can show now that there is an equilibrium here of the weak acid, the solution on the left, and the quantity of acetate ion from the dissociation of the acetic acid is quite small because it is a weak acid. However, the sodium acetate, remember, it dissociates and this reaction goes to completion. So the 0.30 mole per liter of sodium acetate, in fact, has 0.30 mole per liter of acetate ion. So we've just basically taken this equilibrium and we've suddenly increased the concentration of the acetate ion. So now instead of having just a small amount of acetate ion, we have a quite large amount of acetate ion in this mixture. So again, when we look at this mixture, we're going to call that equation 1. There is the equilibrium for it. And the sodium acetate, again, it is not at equilibrium. It totally dissociates. It basically goes to completion. We're going to call that reaction 2. And when we mix the acetic acid and sodium acetate together, that acetate ion concentration is significantly increased from the original amount that was there from the equilibrium involving the dissociation of the acetic acid. So let's start out with the weak acid only here, acetic acid. So let's find the pH of the 0.20 mole per liter acetic acid solution before the sodium acetate concentration is added to it. So the pH should work out to 2.73, and let's see how we do that. So we know we started with 0.20 mole per liter of acetic acid. There was negligible amounts of those substances to begin with. When it reaches equilibrium, the reaction goes from left to right. The acetic acid will go down by X. Hydronium and acetate ion will go up by X. So at equilibrium, the acetic acid will be 0.20 minus X, and the hydronium and acetate ion will be X. So we can use the Ka for acetic acid to calculate what X is, because the equilibrium constant, as always, is the concentration of products divided by concentration of reactants. So it's going to be X times X divided by 0.20 minus X. And to make the question easier to solve to avoid a quadratic equation, we're going to assume that X is negligible. And you can safely do that whenever the original concentration is 100 times greater than the Ka. Well, the Ka is 1.76 times 10 to the minus 5. 100 times greater would be 1.76 times 10 to the minus 3. The original concentration, of course, is greater than 100 times. It's 0.20. So we make that X negligible to solve the equation easily. We can go X squared equals the Ka times 0.20. So X is the square root of the Ka times 0.20 molar. And X is 1.88 times 10 to the minus 3. Now that's the concentration of hydronium ion in this equilibrium. So we can find the pH. It's the minus log of that number. Minus log of 1.88 times 10 to the minus 3 is 2.73. So that would be the pH if it was just acetic acid. And of course, we can find the hydronium ion concentration is 10 to the minus pH. It's 1.9 times 10 to the minus 3. Now, let's consider the salt solution we talked about, the 0.40 mole per liter salt solution, sodium acetate. Again, it dissociates and it releases sodium ion, it releases acetate ion. And again, those two equations, the first equilibrium involving just the acetic acid is equation 1. The second equation is for the complete dissociation of the sodium acetate. And this acetate ion now interferes with this equilibrium, because the Chatelier's principle says if you have one of the participants in the equilibrium added to it, the equilibrium will respond by getting rid of the substance that you add. So that if we add the acetate ion alone to this equilibrium, it's going to cause the equilibrium to shift from right to left. And that is how this solution resists pH change. So when that happens, the addition of the sodium acetate will cause the hydronium ion concentration to go down. And that is going to increase the pH. So this interference, where a common ion is added to an equilibrium of a weak acid, is often called the common ion effect. And it can also happen for a weak base. If you add the conjugate partner of the weak base, as well, you make a buffer solution. So this buffer solution, I guess, draws its name from the fact that the effect of adding acid or base to a buffer solution is minimized by the presence of both the weak acid and the conjugate base partner in significant quantities, so that whichever you add, either acid or base, the equilibrium can respond to it and cause minimal changes in pH. And we're going to go over that in great detail in the next few minutes. So we call these types of solutions, as I mentioned, buffer solutions, where they have a weak acid and a conjugate base partner. So it's a solution that resists changes in pH when you add acids or bases to them. For instance, in the human body, our pH of our blood is maintained very rigidly between a narrow range. If the pH were to leave that region, you could die. And I'll give you an example of when this happens. If you were to hyperventilate, and sometimes people do in situations where they get extremely anxious, what'll happen is the breathing rate will accelerate the rate of CO2 leaving your body. So as the CO2 is an acid, and CO2 is dissolved in your bloodstream. So if you get rid of too much CO2, what happens is the pH of your blood gets altered because you're losing CO2, which is an acid. So the pH will start to rise. And if the pH rises above a certain critical value, you will pass out. And then your breathing will return to normal, and your blood pH will return to an acceptable level and basically save your life. So we have certain innate tendencies our body goes through to ensure that certain critical equilibria are maintained. So a buffer solution is made. Again, you can make one by adding a weak acid and the salt of its conjugate base. For acetic acid, it would be a salt-containing acetate ion. If it was another weak acid, and there are many of them, for instance, carbonic acid, you would have to add a carbonate, like a sodium carbonate or potassium carbonate. Frequently, we use group 1 ions in our salts because in addition to being highly soluble, they also do not impact the pH themselves. They're spectators. Or the other way of making it is to take a weak base and you add a salt containing its conjugate acid. So for instance, a weak base could be ammonia, and to ammonia, you're going to add a solution of ammonium chloride because the ammonium ion is the conjugate partner for ammonia. Now let's look at an example here. So we're going to take 50 milliliters of a 0.20 mole per liter solution of acetic acid and 150 milliliters of a 0.40 mole per liter solution of a salt that has its conjugate base partner, the acetate ion. So we're going to calculate, we already calculated the pH of the acetic acid, and then we found it to be 2.73. Now let's see what happens to the pH when we add the acetate to it. So here is our original weak acid Equilibria. We're going to add now sodium acetate to it. And again, it completely dissociates. The sodium ion is simply a spectator. It doesn't alter this Equilibria, but the acetate ion certainly does. So there's another Equilibria here involving hydroxide ion and hydronium ion to make water, the KW we call that. That can also come to play when we're dealing with buffer solutions. So now let's take a look at what happens to the pH. So we started again with 0.050 mole per liter of acetic acid from our original example. And we know the concentration of acetate ion from the sodium acetate. Well, it was 150 milliliters. It was 0.40 mole per liter. And of course, when we added the two solutions together, the 50 milliliters of the weak acid and 150 milliliters of the salt, the total volume now is 200 milliliters. So the concentration of acetate ion is going to change. And it's now going to be 0.30 mole per liter because of the dilution effect. So we know that this equilibrium is going to go down by X. This side's going to go up by X and up by X. So that at equilibrium, it will be 0.50 molar minus X for the concentration of acetic acid. And the concentration of acetate ion will be 0.30 molar plus X. But again, we can assume that X will be negligible here to make this question easier to solve. And we know the Ka of acetic acid. So we can indeed solve for X, which is the hydronium ion concentration at equilibrium, where you have the weak acid and its conjugate base partner that has been supplied by a salt, in this case, sodium acetate. So the Ka for the acetic acid is 1.76 times 10 to the minus 5. Is going to equal the concentration of X times 0.30 divided by 0.050. And we can now cross multiply and solve for X. And X is 2.93 times 10 to the minus 6 moles per liter. So the pH is the minus log of this quantity. So the pH is now 5.53. So you can see that The acetic acid alone's pH was 2.73, but when I put the buffer in there, the pH is going to rise to 5.53, just as we predicted. Now let's look at a fourth example. Let's see how this particular buffering solution responds when we add hydrochloric acid to it. So here's our acetic acid buffer. We started with 0.050 moles per liter of acetic acid. We had 0.30 mole per liter of acetate. We calculated the concentration of hydronium at equilibrium. We are upsetting it by adding hydrochloric acid. Now remember, hydrochloric acid, being a strong acid, is going to go to completion. So in effect, what we have added is 0.10 mole per liter of hydronium ion from this strong acid, hydrochloric acid. So we're going to inspect this a little bit and see, is there enough acetate ion to resist the addition of the acid? And there is. There's 0.30 molar of acetate ion. If the quantity of strong acid exceeds the acetate ion, then the buffer basically is blown up. The buffer is exhausted. It cannot, there's a limit to how much this buffer can resist a pH change when you add an acid to it. And that limit is, of course, how much acetate ion there is. So let's take a look. When we upset it, of course, Le Chatelier's principle says when we add a substance, the equilibrium is going to shift to use it up. So the equilibrium is going to shift. It's going to go from right to left. And it's going to go down by the quantity that we added. Similarly, the acetate ion is going to go down by the same quantity, and the acetic acid is going to go up by that quantity. So that at equilibrium, the acetic acid concentration will now be the original added to the amount that was created when this system shifted. And the acetate ion went down by 0.1, so it's going to be 0.20. And we don't know what the hydronium ion concentration is. It's going to be at X. So that at equilibrium, what we're going to have is a concentration of acetic acid of 0.15 minus X, hydronium is X, and the acetate is 0.20 plus X. So can we make some assumptions? Well, we're going to assume X, again, is negligible in both instances to save us from a quadratic equation. So now we know the Ka of acetic acid is equal to X times 0.20 molar divided by 0.15 molar, the concentration of acetic acid. And we know X is going to equal the Ka times 0.15 molar divided by 0.20 molar. So X is 1.32 times 10 to the minus 5. We can see the pH is the minus log of this because this is, X is the quantity of hydronium ion at equilibrium. So the minus log is 4.88. So there was a bit of a pH change. It dropped from 5.53 to 4.88. It doesn't completely resist a change in pH, but it certainly restricts the change in pH. Compared to if we just added the hydrochloric acid to water, the pH would drop from 7 all the way down to, in this case, 1. So the buffer does resist a change in pH when we add an acid or base. We just demonstrated that. Now let's consider another example. Let's see what happens to the pH of a solution after I add hydrochloric acid to the buffer to increase the concentration of HCl to 0.50 moles per liter, assuming no volume change, make the question easier to solve. So here's our acetic acid. There is the quantity of acetic acid initially. We calculated the quantity of hydronium ion and acetate ion, so it's the same buffer that we used initially, but this time our upset is going to be 0.50. And now you can see we are exceeding the capacity of this buffer because there's only 0.30 molar of acetate ion. So effectively, we're going to use up all of that acetate ion. And the system will shift from right to left. It's going to go down. It can only go down by 0.3 because that's all the acetate ion that's present. So that concentration will go down by 0.3. This one will go up by 0.3. So at equilibrium, acetic acid is going to be 0.35. This will be 0.20. But acetate ion is in fact 0. So our equilibrium essentially is blown. So the buffer was used up completely. So the pH now we can calculate is the minus log of the 0.20 molar. The pH is all the way down to 0.7 because we added so much hydrochloric acid that we've used up the buffer. The pH in this case went from 5.53 down to 0.7. Now, let's talk about another example here. We're going to add a base to a buffer to see what happens. So we're going to start with the same buffer again. And now realize that, again, there's a couple of other equilibria that are involved here. One of them is this Kw. When I add hydroxide ion, it's going to use up the hydronium ion to make water. And of course, when we use this substance up, what's going to happen is the equilibrium is going to shift from left to right this time. We're now going to use up the acetic acid to replace the hydronium ion that has been used up by the addition of a hydroxide ion. So bases affect equilibria, weak acid equilibria, differently than acids. They affect them in the opposite way, really. They cause the equilibrium system to shift in the opposite direction. So now let's take a look at how this impacts. So we started with the same quantity of the participants in our equilibrium: acetic acid, hydronium ion, acetate ion. We're upsetting it by adding this base to it, this hydroxide ion. It's 0.1 molar hydroxide ion, assuming no volume change. So the addition again of that hydroxide ion, we've discussed, it's going to cause this system to shift from left to right. So in fact, what happens, the acetic acid is going to go down by the amount that's there. It can't go down any further than that. This one's going to go up by that amount, and so will acetate ion. So at equilibrium, again, the equilibrium is blown. There is no equilibrium. So effectively now, the system, we can calculate the pH of this system by simply realizing that the buffer was used up completely. And the concentration of hydroxide ion that's left in the solution, well, we started with 0.10 molar of hydroxide ion, but we used up 0.05 molar because we had enough weak acid here to use up at least half of it. So the amount of hydroxide ion that's left now in this solution, because it's no longer in equilibrium, is 0.050 moles per liter. So the pOH is the minus log of that quantity. So the pOH is 1.30, and we know the pH and pOH are related by pH plus pOH equals 14. So we can rearrange that equation and get pH equals 14 minus 1.30, or the pOH. So we end up with a pH of 12.70 for this situation where we had a buffer that we exhausted completely by adding too much sodium hydroxide. So the pH went from 5.53 to 12.70, significant shift. And remember, each pH unit is a factor of 10. So we really increased the quantity of hydroxide ion simply because we added so much sodium hydroxide. Now let's do an examination quality problem involving acids and bases. So this is basically going to apply the scenarios that we have just learned. So in this case, it's a titration reaction, which you're used to doing in a lab. We are titrating an acid, a base with an acid here. We're titrating sodium hydroxide with the acetic acid, and we want to calculate the pH and hydronium ion concentration of the resulting mixture. So we're combining sodium hydroxide with acetic acid, making sodium acetate and water. So initially, we have to calculate the number of moles of sodium hydroxide. So the 30 milliliters was changed to liters by dividing by 1,000, and we're going to multiply it by the volume, which is 0.100 mole per liter. So we end up with 0.0030 moles of sodium hydroxide. And we're going to do the same now with the number of moles of acetic acid. We're going to use, again, the acetic acid, we know, was 0.100 mole per liter. The volume was 100 milliliters, which is 0.1 liters, and we get a volume of 0.010 moles. So now let's look at this reaction. We know it's a one-to-one reaction from the stoichiometry of this equation. As always with an acid-base neutralization, we get a base and an acid forming a salt and water. So we started with 0.0030 moles, which is the smaller of the two quantities. So it is going to limit the extent to which this reaction plays out. So the acetic acid is not going to be completely used up. We are going to use up only a portion of it, but we're going to make this salt solution. Well, guess what? We are now going to have what's left. We're going to have a weak acid, the acetic acid, and we're going to have a salt of its conjugate base partner, sodium acetate. So what have we just created here? Well, we've created another buffer solution. The buffer involves the equilibrium of acetic acid and acetate ion. Sodium ion is a spectator in this whole process, has no impact on the pH. But to answer our question about the pH of this buffered solution, we have to first figure out the concentration of the acetic acid. Well, we know it was 0.0070 moles, but the volume of the solution is now going to be 30 milliliters added to 100 milliliters. It's 130 milliliters, which can be changed in a liter by, of course, dividing by 1,000. So it's 0.0130 liters of this buffer mixture. So we end up with a concentration of acetic acid of 0.0538 to start with. And the concentration of acetate ion can be calculated exactly the same way. We know that sodium acetate is a salt that goes to completion. The concentration of acetate ion and the concentration of sodium ion will be the same as the original concentration of the sodium acetate. So the quantity of sodium acetate in this buffer mixture to start with will be the number of moles divided by the total volume, again, from adding the 30 milliliters to the 100 milliliters. We end up with a concentration of 0.0231 molar. So let's look at how that impacts this equilibrium. We now know the original concentration of the acetic acid. We know the concentration of the acetate ion. But of course, being an equilibrium, there's going to be a shift. So the acetic acid is going to go down by X. The other side is going to go up by X as the acetic acid, again, being a weak acid as it forms more acetate ion and hydronium ion. So that at equilibrium, the concentration of acetic acid will be 0.0538 minus X. The quantity of hydronium ion and acetate ion will be these quantities respectively. And now we know the Ka of acetic acid. And we are also going to assume, to save us from a quadratic, that X is negligible. So we can say that Ka is equal to the quantity of acetate ion times the quantity of hydronium ion divided by the concentration of acetic acid. So we are going to take the product here and divide it by the concentration of acetic acid, and we're going to solve this equation to get X is equal to 4.1 times 10 to the minus 5. And we know the pH is the minus log of that number, so the minus log of 4.10 times 10 to the minus 5 is 4.387. Okay. Now we've used 3 digits for the pH now, decimals, because if you look at the quantities given in the question, 3 significant digits, 4 significant digits, 3 and 3, we need 3 significant digits as our answer. Now, a much more complicated question. We're going to take an acid called isosionic acid, and we're going to talk about how we can prepare it by heating a solution by heating sodium cyanate in the presence of a solid oxalic acid according to this equation. Okay, so this is our salt, our sodium cyanate. This is oxalic acid. This is the weak acid that we are forming, isosionic acid. And here's a salt. Sodium oxalate is the name of this salt. So now, upon isolating the pure isosionic acid, an aqueous solution of HNCO can be prepared by dissolving the liquid in water. So we're going to find out what is the pH of a 100 milliliter solution of HNCO prepared from the reaction of 10 grams of each of these solids, assuming that all of the HNCO produced is dissolved in the solution. Now, we can't answer this question without the Ka for this weak acid here, this isosionic acid. So first thing we're going to do is calculate the number of moles of the sodium cyanate. that was originally used. So we know it was 10 grams from the question, and we know the molar mass of sodium cyanate. The molar mass is 65.01 grams. So we end up with the number of moles of sodium cyanate, and we can calculate similarly the number of moles of oxalic acid, 10 grams divided by the molar mass of oxalic acid. So we now know the number of moles of each of those two. And we can see from the balanced chemical equation that the sodium cyanate is the limiting reagent, because you can see that if we are going to use up 0.111 moles of H2C2O4, we're going to need twice as many moles of NaOCN. Well, twice as much is 0.222. We don't have enough NaOCN to use up all the H2C2O4. So therefore, we must be using up all the NaOCN. So it's the limiting reagent. So the number of moles, we calculated it. Now let's figure out how many moles of HNCO we're going to make from this reaction. So we know the relationship is 2 moles over 2 moles. So we know the number of moles of sodium cyanate that we started with. So the number of moles of HNCO will be 0.1538 moles, the same as the number of moles we started with. So we're going to figure out the concentration. So the concentration would be the number of moles divided by the volume. The volume of our solution is 100 milliliters, which we changed to 0.1 liters. So we get a concentration of HNCO. And now we know that HNCO, being a weak acid, is in an equilibrium. It's in an equilibrium. It's going to donate one of its protons to water, making hydronium. It's going to leave behind NCO1 minus ion. So initially, the concentration is 1.538 moles per liter. And we know it's going to go down by X because it's going to shift from left to right to reach equilibrium. So at equilibrium, it will be 1.538 minus X. Quantity of hydronium and NCO minus will each be X. And again, we can use the Ka and assume that this quantity here is negligible. The Ka is 1.2 times 10 to the minus 4. It's going to equal X squared over 1.538. So we get a quantity of 1.359 times 10 to the minus 2 moles per liter, which is the quantity of hydronium ion and NCO minus at equilibrium. So the pH is the minus log of 1.359 times 10 to the minus 2. 1.87 is the pH for this equilibrium. Now, this is a much more challenging question that was used on an exam a few years back. I'll read it to you here. Captain Kirk of the Starship Enterprise has been told by his superiors that only an engineer with a knowledge of chemistry can be trusted with the combination of the safe containing the dilithium crystals that power the ship. Now, the combination is the pH of solution A, described below, followed by the pH of solution C. Example, if the pH of A is 3.47 and the pH of C is 8.15, the combination of the safe is 3, 47, 8, 15. Now, the engineer must determine the combination using only the information below. And a big hint here. To answer this question, we need to use solution B to find the Ka for HX. Now, solution B, you'll note, is a salt that has a minus ion that is the conjugate base of the weak acid. So hopefully you realize that the Ka times the Kb of a weak acid and its conjugate partner equals 1 times 10 to the minus 14, or Kw. So we can, in fact, use the pH of solution B to find the Kb of X minus, and then once we know the Kb of X1 minus, we can use it to find the Ka of the weak acid HX. And once we know the Ka of the value of HX, then we can find the pH of solution A. So that's what we're going to head right now. So we're going to do it in steps. So find the Ka for HX from solution B. We know it's a salt. The salt completely dissociates. It's not in equilibrium. It goes to completion. And we knew that the salt was 0.05 0.00 moles per liter, which is the same quantity of sodium and of the X1 minus ion. So we know that the X1 minus is a weak base because it's not from a strong acid, and it's going to be in an equilibrium with water to make HX and OH1 minus. And we know the original quantity was 0.0500 mole per liter. It's going to go down by X. But before we go any further, we're going to use the pH of the solution, because the pH of the solution is going to tell us the quantity of HX at equilibrium. In this case, we're going to use the pH to find the pOH, because we know the pOH is really the concentration of hydroxide ion at equilibrium. So if the pH is 10.02, we know by subtracting that number from 14, we get the pOH. And if we know the pOH, we know the concentration of hydroxide is 10 to the minus pOH. So 10 to the minus 3.98 is 1.05 times 10 to the minus 4, which happens to be the concentration of hydroxide at equilibrium. Well, where did the OH minus come from? It came from this system going left to right. The system cannot make just OH1 minus. It has to also make HX, the same quantity, because it's a one-to-one relationship. So the quantity of HX will be the same number, 1.05 times 10 to the minus 4 moles per liter. And that quantity went up in both cases from a negligible amount to start. So X went down by that amount. And at equilibrium, it was 0.050 minus that same quantity. But again, we're going to assume the 1.05 times 10 to the minus 4 is quite a bit smaller than 0.05. So we are going to assume it's negligible to make the calculation easy. So KB is 1.05 times 10 to the minus 4 squared divided by 0.0500. And KB is calculated as 2.196 times 10 to the minus 7 moles per liter, because this is moles per liter squared divided by mole per liter is a mole per liter. Now, we know KB for the weak base, X1 minus. We can now find the Ka for its conjugate acid partner, HX, because we know the Ka times the Kb is equal to Kw. We rearrange the equation, so Ka is Kw divided by Kb. We take Kw divided by Kb, and we get the Ka for the HX, the weak acid, in solution A. Well, now we are ready. In our 50 milliliters of solution A, we know the Ka. The equilibrium is the weak acid plus water makes hydronium and X1 minus. We knew the original concentration. We know it's going to go down by X. We know this is going to go up by X, so that we can use the Ka, which we just figured out, 4.56 times 10 to the minus 8 equals 8 squared divided by the original concentration. We're going to assume it's negligible again, so that eliminates the quadratic equation. So now we get X equals the square root of the Ka times the concentration. That works out to be 6.75 times 10 to the minus 5 moles per liter. And the pH is the minus log of 6.75 times 10 to the minus 5. The pH is 4.17. So we now have the first two numbers in our combination to get at our dilithium crystals. Well, solution C is made by adding 15 milliliters of a base, potassium hydroxide, a strong base, and its concentration is 0.25 moles per liter. We're going to add that to solution A. So the number of moles of the weak acid is 0.0500 liters. That's 50 milliliters. And the original concentration was 0.100 moles per liter. So the number of moles is determined by concentration times volume. So we get the number of moles of HX in our solution C. The number of moles of potassium hydroxide, well, you were given the fact the solution of potassium hydroxide was 15 milliliters, which we've changed to 0.0150 liters by dividing by 1,000. Its concentration was 0.25 moles per liter, so it's 0.250 moles per liter. So by multiplying concentration times volume, we end up with the number of moles of potassium hydroxide in solution C. So we have our weak acid, we have our base, and this reaction is going to go to completion. It's not an equilibrium, it's an acid-base reaction. So the limiting reagent in this case will be the potassium hydroxide. It's present in smaller quantities. So that at equilibrium, the quantity of HX will be 1.25 times 10 to the minus 3, which we got by subtracting 3.75 times 10 to the minus 3 from 0.00500. And the quantity of KOH is 0. Quantity of KX is 3.75 times 10 to the minus 3. Well, what do we have now? It looks like we have a buffer here. So the concentration of HX in this buffer is the molar quantity divided by the total volume. Now, we added, remember, solution A to solution C, which was 50 milliliters added to 15 milliliters, it's 65 milliliters. So the quantity of HX in our equilibrium involving our weak acid and our conjugate base partner, X1 minus, is going to be 1.92 times 10 to the minus 2 moles per liter when we added those two solutions together. So the quantity of the X1 minus, which is the conjugate base partner for our weak acid, again, is 3.75 times 10 to the minus 3 moles divided by the total volume when we added the two solutions together, 50 and 15, 65.065 liters. It's going to be 5.76 times 10 to the minus 2 moles per liter. Well, in the buffer solution, again, we've established we have the weak acid, HX. We have the conjugate base partner, X1 minus. They're both present here in those quantities, which we just figured out. We know as a buffer, it's going to, the HX is going to, some of it will get used up. In this case, a very small amount. And it's going to make a very small amount of the X1 minus. So that at equilibrium, for all intents and purposes, the quantity of HX will be equal to the original amount that was there. And the quantity of acetate ion, or sorry, not acetate, but X1 minus, is going to be the same as the original amount that was there. So that we know the Ka of the weak acid. We figured that out earlier. We know the Ka will be equal to X times 5.76 times 10 to the minus 2 moles per liter divided by 1.92 times 10 to the minus 2 moles per liter. So X can be solved now by solving this equation. So X will be equal to this product divided by 5.76 times 10 to the minus 2. And that quantity works out to 1.52 times 10 to the minus 8 moles per liter. And that, again, is the quantity of hydronium ion in that buffer solution. So we now can say we know the combination because we know the pH will be 7.82, and the combination again was the pH of solution A, 417, and the combination follows with the pH from the last solution C, which is 782. So sorry about the little glitch at the end there. I hit a button, wrong button. It revealed all the numbers there. So I'll just put them back up in case you're distracted by those animation numbers. So let's show it again. That's where we left off. So there's our combination. And as always, there is going to be homework. These questions are not that easy, so please practice them. There's problem set number 5 that is on the OnQ site. Read Petrucci, those pages, and study these examples, and please practice these problems. Thank you. Signing out now.